So in this video on work and energy, we want to look particularly at energy. And the energy of a body is simply its capacity which it has to do work. The energy of a particle is its capabilities to do work. When a force does work, it changes the energy of a body. So for example, when we act against friction, when we're going over a rough surface, energy is used up getting over the friction, and so energy is lost by the body. Or if I push something along or have an engine in it, then energy is given to the body and it'll get quicker. And we're going to look at two types. There's lots of different types, but the main two that we will look at, potential energy and kinetic energy. I'm looking at kinetic energy first. It's simply the energy of a body that is due to its motion. Okay. The formula for finding that kinetic energy is fairly straightforward. It's a half mv squared, where v is the velocity and m is the mass of the body. So when a particle is at rest, its velocity is 0, it has no kinetic energy. It is not moving, and so it has no energy due to its motion. And what we will see is that we can see that if something increases its kinetic energy, then that's the work done by that body. So if we find the work done, we can say that will give it an increase in kinetic energy. So for example here, a car of mass 1200 kilograms starts from rest at a set of traffic lights. After travelling 300 metres, its speed is 20 metres per second. Given that the car is subject to a constant resistance of 400 newtons, find the driving force, which we assume is constant. Now this is something that we could do just using our UVATS equations and Newton's second law quite easily, but often you may find a question where it says using energy considerations, and so you have to solve this using kinetic energy. But first, as always, a diagram is usually helpful. So here's our car. It's got a mass of 1200 g, sorry, a weight of 1200 g, and normal reaction going up. Constant resistance of 400 newtons, and we have this driving force of the car, which I'm just going to call D. Okay, quite a straightforward diagram to start with. I know that the work done here is equal to the overall force in the direction of motion times the distance travelled. And in this case, the distance travelled is 300 metres. The overall force in direction of motion, well, if it's going this way, then D minus 400 is its overall force. And that's the work done. Now, since it started from rest, the increase in kinetic energy would just be got by finding its final kinetic energy, because its initial kinetic energy, KEI, I'm going to call it, is 0. The final kinetic energy, KE, let's call it F, we subscript, is based on a half mv squared, which is a half times 1200 times and 20 squared, which is 400. And that then is 240,000 joules. Now, I know that the work done is the increase in kinetic energy here, and so I can put these two things equal to one another and say that 300 upon D minus 400 is equal to 240,000 joules. So D minus 400 is equal to 800, and so D is equal to 1,200. D is a driving force, so the units there are newtons. Now, I guess we could have done it, like I said, by UVATS equations. You know, if we said that S is 300, U is 0, its initial speed, A we don't know, and V is 20. Then we could have used V squared equals U squared plus 2AS. And when we put that in, we get 400 equals 0 plus 600A. And we get A to be 2/3. Once we've done that, we would have said, okay, using Newton's second law, F equals ma, then D minus 400 is the overall force. That's 1200 times 2/3. So D minus 400 equals 800, and so D is still 1200 newtons. So we still get the same answer either way, but like I say, you could be asked specifically to do this by energy considerations, in which case you would have to use your work done and your kinetic energy. The second particular type of energy that we're going to look at, and quite often they call the two together, mechanical energy, potential energy, and kinetic energy. But the second type then is potential energy. And that's the energy of a body due to its position. Generally, its height above a given level. And that potential energy is got by mgh. And we see that if we're going vertically, the work done vertically is the increase in potential energy. If something goes down, if it's dropped, then its potential energy decreases. So as something gets higher and further up, it has a larger potential energy. As it comes down, it's smaller. And we get to choose where our zero level for potential energy is, and sometimes we can make life a wee bit easier by choosing a sensible point, but it really doesn't matter as long as we're consistent. So for example, a child of mass 25 kilograms slides 4 meters down a smooth slide inclined at sine theta equals 3/5 to the horizontal. Find the potential energy lost by the child. Okay, so imagine then we have our slide coming down, and the child has gone down that slide. It's an angle theta, and we know that sine theta is 3/5. So if we did a little triangle and that, where opposite is 3 and hypotenuse is 5, that's 4. Very quickly, if we needed to, cos theta is 4/5, and tan theta would be opposite over adjacent, so 3/4. Okay. But we know that this slides 4 meters down a smooth side, so just need to be careful. This is the distance slide, not the height, not the vertical height. But we want to find that value h. And that value h then is going to be got is 4 sine theta. Now again, we know that sine theta is 3/5, so that's 4 times 3/5, which is 12 over 5. Now, the loss in potential energy is going to be mgh. So I'm going to treat, just for this one here, that this level here is where my potential energy is equal 0. And so anything below that, it's going to lose potential energy. What I could do also, if I wanted to, is, let's scrub that. Let's say this is my value, potential energy equals 0. That's where its final resting place is, at this bottom level. Goes from here to here. This is where its potential energy is 0. It will have started with more potential energy. So that's mgh. The child is 25 kilograms times g times 12/5, which is what we worked out h to be. And that then works out as 60 g joules. And if we want to put that into 3 significant figures, 588 joules. So between the top of the slide and the bottom of the slide, it has lost 588 joules simply due to its position. Up here, it had 588 joules more than down here.